Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hopefully you guys had a good weekend. Let's jump into it. Oh, this thing locked out. Okay, all right. And make sure I can see the chat here and everything. Okay, all right, cool. Let's jump in. Last time we solved the rate problem. Very interesting. Okay, so let's just actually do some recollection here. So recall, last time we developed the limit f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. This was called the derivative of f of x with respect to x, which you don't always have to say that part, especially if you're in Calc 1, but it becomes important once you're at Calc 3 and above. It's called derivative of f of x with respect to x. And so, yeah, let's talk about notation. I think I really expressed that last time. So there's Newton's prime notation, two main ones. If y equals f of x, then you have something called Newton's prime notation. And that's this guy. So this thing here is called a prime. And this is, it's read f prime of x, or just f prime for short, right? And it really just means the derivative, right? It is the derivative with respect to x, right? And that's the guy I put in this thing here. There is another notation. This is called the Leibniz notation. So remember I told you calculus in different isolations or incarnations or whatever, we've been doing it for millennia, right? But Newton and Leibniz, these were the guys, around 300 years ago that really kind of made it into a cohesive theory, a kind of study that we do today. And they developed it separately. There is a feud as to whether Leibniz copied Newton's work or whatever, but in theory, he developed it separately, but he came out with it after Newton did. So they both were working on this problem and they came up with calculus. Newton was more concerned with figuring out calculus in order to solve problems in physics, whereas Leibniz was more of a mathematician. He was more mathematically inclined. And so he actually came up with a nicer theory in terms of the mathematical applications of it. And he came up with another notation, which is pretty cool. dy dx, right? And that's how you pronounce it. Right? It's read dy dx. not dy over x or dy divided by x. We call it dy dx, and everyone knows that's what you're talking about, right? And basically, it comes from the fact that, you know, delta y over delta x, this was the slope of the secant, right? Of course, delta is a Greek letter, and all he did was just change the letter to the English alphabet, and so he called it dy dx. This is the slope of the tangent. And remember, this guy approaches that as delta x approaches 0, right? So that's where the notation kind of comes from. He took delta y over delta x, change in y over change in x, rise over run. He just wrote it as dy over dx, right? So that's the Leibniz notation. Both of these are used pretty commonly. For the most part, I will be using Newton's prime notation, not because it's better, because it's actually not. The Leibniz notation is actually way more useful. It turns out that this notation, you can actually kind of treat it like a fraction itself. You could separate the dy and dx's and actually figure out a lot of problems that way. So it's actually a much more functional, pardon the pun, maneuverable notation. But for the most part, I'll be writing the Newton's prime notation because it's just easier to write down, and that's literally the only reason why I'm going to use that most of the time. One other thing, just to hit home what we spoke about last time, interpretations. Okay, so when we say f prime of x, what do we mean? What are we talking about? Yes, this is the derivative of f. But what does it mean to be the derivative? Well, you can think of it as the slope of f at x, right? So you can actually think of slope and derivative essentially as synonyms. Synonyms. I forgot how to spell synonyms wrong. Okay, so it's essentially the slope, right? So it's the slope of the function. What does it mean to be the slope of the function? Well, it's the same as saying it's the slope of the tangent line. To f at x. Another way you can talk about it is it's mentioned as the instantaneous rate of change. Instantaneous rate of change. It's how fast f is changing at an instant. Another way you can think about it is in terms of just what it does. It can tell you how fast y equals f of x is changing in relation to x at some instant. And it gives you a formula for the above, right? So it's interpreted as slope, or more specifically, you can think of it, well, it's the formula that will tell me what the slope is at something, right? So these are all important interpretations, and this will tell you when you might want to use a derivative, as well as some things I'll be talking about later. So you would have, if I ask you, for example, in a question, hey, here's a function, find the equation of a tangent line, you should know the derivative is going to be involved in that because you have the interpretation that it gives us the slope of the tangent line. So you knowing that it's the slope of a tangent line, you know whenever someone asks you to find a tangent line, the derivative is going to be involved, right? So for example, so the interpretations here, they are useful, they're important to make sure you know how to answer certain questions when you would want to use a derivative versus not, example, things of that sort. Any questions on that so far? So yeah, those are really just facts to know, really. It's not so much something to understand, but let's actually do some examples. So the first example is a very important one. So it's a very traditional example. It's a very traditional example. So it almost doesn't matter where you take Calc 1. If you take Calc 1 virtually anywhere, there's going to come a point where they're going to ask you a question pretty much exactly like this. Right? It's coming on your first test. It's definitely coming. You should expect it. It's very traditional for us to ask this question. Okay, so let's actually compute it, right? So we know the formula to find the derivative, but let's actually use it and do something very simple, right? So here's an example. Use the definition of the derivative to find f prime of x for this function. The function is y equals x squared. Okay, and then of course part B, use your answer to part A to find the equation of the tangent line to f at the point where x equals 3. Okay, very standard Calc 1 vanilla questions, very, very traditional question. Okay, and we're going to do it. So it's also worth mentioning that when it says, if I ever say to something like use the limit definition or use limits, then no credit would be given for any other method. Right? So the point of this question is specifically for you to use the definition. Eventually, not today, but eventually, I'm going to give you a lot of shortcuts and formulas that are going to allow you to find derivatives without going through a limit formula. And so that comes later. But for now, I actually want you to get used to using this formula because I'm specifically going to ask you to use the definition to find derivatives. Okay, and we're going to start with x squared. Also a very typical example. Almost everyone who starts the first example is going to be y equals x squared. It's the only function that's not so simple that it's like kind of trivial where it doesn't even make sense to even talk about it, like x. Like, what is the derivative of x? Well, it's 1. How do you know? Because y equals mx plus b. M is 1 here, right? You kind of know the answer. It's kind of silly, right? Y equals x squared is not that obvious. And it's also not so complicated that you're going to get lost in the minutiae of me going through the example. So it's, again, very common example to be a first example. So let's actually jump into it. And of course, since we're using the definition, you're obviously going to have to remember the definition. I even asked you this on a quiz. So we keep writing the definition until we memorize it. So that is your f of x. So this means that your f prime of x is going to be the limit as h approaches 0 of f of x plus h minus f of x over h. Now, this should not really be a big deal because literally on day 1 of the class, we did examples like this and even more complicated examples than this, I believe. So remember what f of x plus h means. Every I see an x, you put x plus h instead in parentheses. Make sure you don't do anything silly like cancel across sums or distribute powers across sums or divide by 0 or anything like that. But afterwards, you just go through with the algebra. So here you're going to have x plus h all squared minus x squared. You can put parentheses around the x squared if you want, but not necessary. But it's not wrong if you want to do it, over h. So we're going to now want to take that limit. So now we have to remember our limit strategies. Obviously, you want to try to see if you can plug in at first. Never going to be the case when you set up the derivative because there's an h in the denominator. So you can't immediately plug in, but your goal would always be to, of course, try to simplify so I can plug in. That would mean I would want to expand this x squared plus 2xh plus h squared minus x squared over h. X squares are going to die. Then you'll notice that I would have a common h in the top that I can factor out. That's going to die. And so now we would have essentially the limit as h approaches 0 of 2x plus h. And now notice I can plug in h equals 0 without any repercussions. I'm not dividing by 0 or anything crazy is happening. You get 2x. That's it. So it turns out that f prime of x equals 2x. Now, while we're here, let's talk about expressing this while we're here. how to express this. There are a couple ways. The first way is longer, and therefore, because I'm too lazy to have to write down a lot of stuff, I'm going to not use it very often. So one way is to say, well, if f of x equals x squared, then f prime of x equals 2x. So one way you can express it by that sentence, right? Or something like f of x equals x squared means that f prime of x equals 2x, right? Or Jhevon's preferred way. Can't write my name on this thing. You can actually use the Leibniz notation and write it out. So you can actually use in one little phrase, d dx of x squared equals 2x, right? And that literally means the derivative of x squared with respect to x, right? So when you have, right, since dy dx equals, you know, the derivative of y with respect to x, where my y is this guy and my x is that guy, right? So it's always the derivative of the top variable with respect to the derivative of the bottom variable. It means that the bottom variable is the independent variable. It's the guy that's on the horizontal. But we can also say, but dy dx, you can think of this as d dx times y, right? And you kind of think of it like a function. So this is like the derivative with respect to x of y, right? And so you can literally replace that function y with whatever function you happen to be concerned with at the time. So in our case, that y was x squared. And so I can think of this as the derivative with respect to x of x squared, right? And we know that that is 2x. Okay. Now, what does it mean to say that the derivative is 2x? Well, it means everything I told you up here. It means that the slope of the function is always given by a formula 2x. The slope of the tangent line is given by 2x. The instantaneous rate of change is given by 2x. You want to know how fast the y is changing with relation to the x? Well, it's changing twice as fast. That's how fast it's changing, right? So that's what the 2x actually means. This means, for example, if I want to know what is the slope of the tangent line when x equals 1, I would plug in 1 here and I would get 2. Some would say the answer is 2. What is the slope of the tangent line when x equals -3? Well, it's -6, right? I just plug it in. Like whatever I want to know, whatever point I care about, I can plug it in. This is a formula that will give me that information. This is a very short way to actually express that that's what I'm doing. The derivative with respect to x of x squared is 2x, right? So yeah, so that's a while we're here. Okay, now let's go to B. So now B asked us to find, using your answer to part A, find the equation of the tangent line to F at the point where x equals 3. Now, what I do want to emphasize here is a tangent line is just a straight line. Don't let the name scare you. Sure, it's a straight line in a particular context, but it's still a straight line. right? So we can find it given its slope and a point or 2 points, etc. Of course, that latter part doesn't apply here, right? Because we don't have 2 points. We have 1 point, the point where x equals 3. Okay, so just as a general rule, right? So if I say tangent line, don't get, oh my God, it's still y equals mx plus b, the same guy. The only difference is the m comes from somewhere special. The m comes from the derivative. And that's all it is. A tangent line is just a line where to determine the slope of that line, you use the derivative, right? So let's see, what is our point? Well, we know x is 3. When x equals 3, this means that your y is equal to 3 squared because we're looking at x squared. So the point is x1 comma y1 equals 3 comma 9. So that's the point. You get the point? Okay. All right. So now we go with what's the slope? So here's where you use the derivative. Here's where you use your answer to part A. M is equal to the derivative evaluated at x equals 3. I can just think of it as a formula or a function. So what is that? Well, it's just 2 times 3 because the derivative is 2x, right? So this is i.e. f prime of x equals 2x and plug in 3. Plug in x equals 3. So that leaves us with 6. So now I know the slope and I know a point. I can use a formula. Tangent line is going to be, well, y minus y1 equals m x minus x1. So the y1 was 9, the m was 6, the x1 was 3. That is your tangent line. Or, I mean, if necessary, which is not always or required, we can solve for y. Put it in y equals mx plus b form. That's going to be 6x minus 9, I think. Because you have 6 times 3, which is 18. 6 times minus 3 is minus 18. Then I add 9 to both sides, so I have minus 18 plus 9, so it's minus 9. This is the mx plus b form. So this is what we call the point slope form. Right. So we learned that in pre-calc, and this is called the slope intercept form. Right. Now, if I don't tell you what form to put it in, then you're not required to put it in a particular form, right? You just do whatever, and so you could leave it as the top one. That'll be fine, right? So if I specifically say, make sure you put it in slope intercept form or something like that, then you'd have to do this. But otherwise, I wouldn't waste the time, right? Or if I have give you a bunch of multiple choice options, then you rewrite it so that you can match it up with the option, right? So if the options are in the mx plus b form, you write your answer in mx plus b form. If the options are not, write it in the other form, like write it as something else. Okay, so that is the question. Any questions on this? Concerns, issues, anything you didn't understand? good. Yes, no, maybe so. Sign of life out there. I guess very good. Let's do some more examples. Where are we? Two. Okay. Okay. So using limits, which means you have to go through that definition I just gave you, the limit as h approaches 0 of the difference quotient, find the derivative of the following. So just as a concept check, what is the answer going to be here? Turns out you can know what the answer is going to be before you even do it, if you're really understanding what the derivative is about. Y equals c, where c is a constant. So like y equals 5, right? Or y equals 7, or y equals 13, or y equals pi, y equals a number, right? What would be the derivative of such a function?
C?
Well, let's see. What does y equals a constant look like? If you were to graph it, what does it look like?
Horizontal line going through the point.
Is it just me, or is there a lot of interference? Because I couldn't hear you. Claudia, I don't know what's going on with your mic.
Sorry, I think it was my AirPods.
Okay.
Horizontal line going through the point.
It's a horizontal line going through C, right? So let's say for whatever reason, C is like here, right? That's C. So you'd have just a horizontal line going through C, right? Now, what does the derivative mean? How would the derivative relate to this graph? The derivative is what? What is the derivative? What is the interpretation?
The slope.
It's the slope, right? So me asking you, what is the derivative of y equals c, is the same as me asking you, what is the slope of a horizontal line? Well, what is the answer?
So it's 1 then, right?
It's what?
1.
No.
Up 0.
It's 0.
0,
Slope
yeah.
of a horizontal line is 0. So it turns out the answer is 0. I know that. So, hey, slope is 0. This means the derivative of the function c should be 0. We should get that answer. We should know that's the answer, right? Because it's slope. That's what it is. That's what the derivative is. Okay. So now let's see if going through our definition actually gets us that answer that we know we should get. So here we have f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So what is f of x plus h when y equals f of x equals c? Well, it's just c, right? There's no x to plug in. So f of x is also c, so it's c minus c over h. Well, that's just the limit as h approaches 0 of 0 over h, which is just the limit as h approaches 0 of 0. What is the limit of a constant? Well, it's just the constant. That was one of the properties. So it turns out that it's 0 as expected. In fact, this is like a rule that we can know now. The derivative of a constant is 0. Right? This is like a rule. Right? Derivative of a constant is 0. Right? Doesn't matter what the constant is, right? So if I say derivative of 7, what is that? 0. Derivative of 13, what is that? 0. Okay, all right, let me try to trick you now. What is the derivative of 2 raised to the 3 plus radical 7 divided by 1 plus radical 4 minus 9 to the 32? That looks super complicated. It's 0. It's a constant. There are no x's in it. There are no x's in it. If there's none of, if this guy isn't showing up, it's a constant. The answer is always going to be 0. Derivative of a constant is 0. Doesn't matter what the constant is. Okay, that was the first example. Right. Let's look at this one. Okay, now suppose we have the function c times x. What is the derivative? What is the answer here? This is also one that you can tell without even doing the calculations. So c is just a constant. So if I ask you y equals 5x, y equals 7x, y equals 12x, what is the derivative?
0.
Oh, somebody was gone.
I can't hear you. What did you say?
0.
0?
It's a constant.
It's not a constant. Look at the function.
I was thinking x.
There's an x in it, right? So it's not a constant, meaning when the x value changes, this thing changes. Unless your constant is 0 itself. So it's not a constant. So
it's C
X.
then? Sorry.
it's c, right? So if I have y equals cx, right? That is the same as saying y equals cx plus 0. That is like mx plus b. M is the c, right? And we know that the derivative is just the slope, right? So it's the c. So here, if you have like y equals cx, it's going to look something like just some line passing through the origin with slope c. Here your c is positive, but it doesn't have to be. But that's the idea. C is the slope. It is in the role of m. So if I have a constant times x, the derivative is the constant, whatever the constant is. Doesn't matter how ugly the constant looks, how big it looks, how complicated it looks, doesn't matter. You have a constant, a number, times an x. So you have something that looks very complicated potentially, but has no x's in it, and there's an x right beside it. The derivative is just the thing in front of the x, right? Okay, so how do we know this is true? How do we prove this? Well, we can go back to the definition of f of x plus h minus f of x all over h. If, how much time do we have here? If our f of x is cx, well, that means this is c times x plus h minus c times x all over h. So I would expand this. CX's cancel each other. So I would now have the limit as h approaches 0 of ch over h The h's cancel each other, and I'd be left with the limit as h approaches 0 of c. We already have a limit property that tells us that is the constant. So yeah, as expected. So I can say this means the derivative of a constant times x is the constant. And you can take this as another rule. So derivative of 7x is 7. Derivative of 1.2x is 1.2. The derivative of 1 minus radical 2 over 13 to the 9/2 plus 12 times x is 1 minus radical 2 over 13 to the 9 over 2 plus 12, right? The idea is, if it's a constant times the x, the derivative is just a constant, because the constant is in the position of m. M is the slope. Derivative is literally a synonym for slope. Derivative is kind of like a generalization for slope. We use the word slope if we're talking about straight lines. If we're talking about, in general, slope of anything, including straight lines, we use the word derivative, but it really just means slope. So we can know what the slope is, right? In particular, the derivative with respect to x of x is 1. Just a nice thing to know. Derivative of x is 1. Okay, so it's going to come a point where you're going to see why knowing that is going to be important. But knowing the c times x is c is equivalent. Probably better to even know the more general one, but whatever. Derivative of x is 1. Why? Because m is 1 in the mx plus b, right? It's m is 1 and your b is 0. So yeah, that is that example. Now, talk about these guys down here. Kind of match up the scale here. I think this was right on the edge of the page. Like sometimes I mess up the scale and it's like some parts of the notes is like I write huge and some parts I write small. Okay. I don't know if there's like a setting to save what magnification I want it as a preferred. Probably not. That would be too convenient. Okay, so here's another example. Now this one you might realize is not so straightforward. Here, the graph looks like this, right? So you're like, well, what is the slope of that? Right? It's just, that's kind of weird. Like, I don't know. Like, it's not a straight line, so it's not in mx plus b form. And this thing is like curves and it's just like this asymptote in the middle. Like, what is going to be the slope of this, right? So again, we will go by the definition because we want to get practice in that. Because Jhevon is definitely going to ask us this on the first test. So f prime of x, we will write out what it means because that's how we're going to remember it. So now, this means 1 over x plus h minus 1 over x all over h. That's going to be what happens when you plug it in. And pretty sure we discussed this already. This is what's called a compound fraction. Quickest way to deal with it is to multiply and divide by the LCD. So I'm going to multiply by x times x plus h divided by x times x plus h. I'm going to divide this here, and this part is going to distribute. In the first case, the x plus h's would cancel. I'd just be left with x. In the second case, the x will cancel. I'll be left with x plus h. So that's what that becomes. Of course, here, your x is going to kill that x, and I will be left with just a minus h in the top. And the h is going to cancel. And so I would have And at this point, I can plug in h equals 0 without anything detrimental happening because of the h. And we get that. So of course your x can't be 0, but hey, your x couldn't be 0 in the very beginning anyway, so it's not an issue. But that would be the derivative. That guy gives you the slope. So it turns out the derivative of the function 1 over x is minus 1 over x squared. You can take that as a rule, but you don't really have to, because I'm going to actually do something where you can know about things like this more generally pretty soon. But if you want to memorize this, I won't stop you. I don't think it's necessary though. So there are a lot of extremists. They either believe that, you know what, you should memorize as much, you should learn everything by rote so that you're very quick with it and learn everything. And then there are other people like, well, you need to understand what's going on. You have to find the longest, most drawn out way to show that you really understand. I'm kind of a mixture. I say you memorize when useful, you don't memorize if it's not, right? So there are certain things you want to memorize. This isn't one of them. If you're someone with not a good memory, as myself, then you memorize when you have to memorize something. You memorize just as enough to be efficient, right? And if I'm going to memorize something that covers all these other cases, I'm not going to memorize those cases. I'm just going to memorize that one thing and know that it will cover all these other cases. So there's going to be something I'm going to show you guys that's going to cover multiple cases, including this one. So if you memorize that, you'll automatically memorize this. So you can memorize this if you want, but I wouldn't really sweat it. But yeah. That's that one. Okay, last example, the square root. We're going to do this all again at this point. So again, now we have here the square root, looks like this, right? Like slope. Well, let's see what the slope is. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is going to be the limit as h approaches 0 of x plus h minus square root of x all over h. This is again a very common situation. This is where we multiply and divide by the conjugate. I'm going to multiply by x plus h plus radical x over x plus h plus radical x. And this is going to multiply that. And this is going to multiply by that. And we know that the conjugate, the whole point of that is to take advantage of the difference of squares formula in the case that we have squares roots. So the top is going to become the first part squared minus the last part squared. And remember, as I told you long ago, never expand the denominator. So I'm just going to leave that factored. The x's will die, of course. And I would have h divided by h times x plus h plus radical x. Because the denominator is still factored, I can see that I need to cancel that. So we have that. Now I plug in h equals 0, and I would just get 1 over radical x plus radical x, or as it's sometimes called, 1 over 2 radical x. And that is your answer. And yeah, so the derivative of the square root of x is 1 over 2 rad x. Again, can take this as a rule if you want. Radical x is fairly common. So if you want to memorize it, you can. I don't think you have to though. So yeah, do with that as you will. So yeah, there are some examples, right? Just reminding you of this stuff because there's definitely going to be a question that I'm going to ask you that's going to be like this one, where I'm going to ask you to use the definition to find the derivative and then find the tangent line. And so you really want to remind yourself about how do you do difference quotients, how do you simplify, how do you take limits. We're putting together a lot of things that we've been doing since day one, actually. Limits we learned fairly recently, but we knew how to simplify difference quotients since day one. All right, hopefully that was understandable. I went through kind of quickly, but again, that's because we kind of been doing this quite often. Just we're doing it in a different context now. I'd like to talk about some interpretations of the sign of the derivative. Okay, so let's look at some examples. Let's say this, 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 right? So let's say I have a line here that looks like so. I have a line here that looks like so, horizontal. I have a line here that looks like so. I have a line here that looks vertical. Now, if I were to ask you, tell me about the slope of these lines. What could you tell me about the slope in the first situation in terms of what sign it's going to have?
Positive.
Positive. What about the second one?
No slope.
No. I think I know what you want to say, but technically it's not correct.
Isn't it what we talked about with the constant?
Yeah, but what is the slope? Tell me about the n.
0.
It's 0, right? It's not the same as saying no slope. What about this, the third one?
M is less than 0.
M is less than 0. What about this one over here, the last one?
It's 1.
No.
And, no slope.
This is no slope. So here, M is undefined. As in, there is no slope. It's not even a thing in this context. So, right, vertical lines don't have slopes, right? Because rise over run, what's the run of a vertical line? 0. If you could find a slope, you would be dividing by 0 for a vertical line. So what does that mean? So it means in this case that my derivative is positive. This means that the derivative is 0. This would, of course, mean that the derivative is negative, right? This would mean that the derivative is undefined. So we can generalize this. Notice that if you have a function, let's say it's doing this, so it's not a straight line anymore, it's a curve, or it's doing this, and you were to say plot a tangent line, then it looks like a straight line with positive slope, which means the derivative is positive. Here, this guy looks like a line with negative slope, which means the derivative is negative. And one thing I want to point out to you here is, note here, positive slope. And what that means is the function is going up as you move from left to right. We call this increasing. Right? Goes up as you go from left to right. Right? And here you have negative slope. But what's happening to the function? It's behaving like a line of negative slope, which means it's going down as you go from left to right. We call this decreasing. And that means it's going down as you go left to right. And this leads to the last two facts, and then I'll let you go, is that if f of x let I be an interval, then we know two things. If f prime of x is greater than 0 on I, then f is increasing there. And if f of f prime is negative on I, then f is decreasing. So we developed the notion of a generalized slope, but it turns out that we can actually talk about the property of a function. If it's going up from left to right as I move from left to right, or down from as I move from left to right, I can actually describe this in terms of the sign of a derivative, which is actually going to be super important. So we can tell when a function is increasing or decreasing by looking at the derivative. And we're a couple minutes over time, so we'll stop there. Next time I'll talk a little bit more about properties of a derivative as well as higher derivatives. It turns out that a lot of times you can actually repeatedly take derivatives. Like I can take a derivative and then I can take a derivative up the derivative and a derivative up the derivative. And these guys are actually very useful in applications as well. But that being said, we are going to stop there. I think that's it, yeah. So yeah, as always, I'll post this later and you'll have the notes, but that is it. Okay, thank you for your attention. Hopefully that was clear. I'll let you guys go. I will see you guys tomorrow in the next one. Ciao.
Thank you.